Welcome to another module of this course, Microwave Integrated Circuits. We are now in week 6 of this course. So far all the circuits that we have considered were basically passive circuits. So passive circuits are one which do not produce or circuits where the output power or rather I should say passive circuits are one which don't require an external power supply. Whatever power they need for their operation comes from the input itself. So they don't need an external DC source for their operation. But then active circuits are one which for their operation separately need a power supply. So it can be a DC bias circuit, or it can be directly, the device can be directly connected to power supply. Now active circuits, some common examples of these active circuits are amplifiers, mixers, and various other active circuits that are used. So now when active circuits, when we are considering active circuits for microwave engineering, there is often the problem of impedance matching. That is, we make a device, but it has to be properly input and output matched to minimize the reflections. How do we do that? So in this module, we will be studying about how these impedance matching networks are designed. Now you may be wondering why impedance matching is so important. It is important because impedance matching is the main determiner of how much power will flow through an active device. It's true that there are other intricacies within the device, for example the biasing and then how the active devices should be arranged within a circuit. But most of the circuits, for example if we are designing an amplifier circuits for microwave engineering, it might be a simple say NPN or your PMOS or NMOS type circuit, and once the circuit topology is fixed, all that is left to be designed is the input and output loading to that circuit. So let us consider how to do this design of this input and output matching circuit for active devices, specifically 2-port amplifiers. So let us consider first, we have already studied our Smith chart in the previous lectures. Just to review it once again, we have two types of Smith chart. One is the Z Smith chart, other is a Y Smith chart. And then when we combine both, we get what is called a ZY Smith chart. Now suppose we have a load connected. Let's consider a simple load ZL, and say its normalized impedance is this. So this small z is equal to this, and we now connect an inductor in series like this. So, this is an inductor having a normalized impedance small ZL, and so when we connect this small ZL, how does the input impedance change? This point here represents our impedance Z given by 0.5 minus j 1.0, and we have connected an inductor in series with this impedance as shown. Now recall that when you connect an inductor in series, then we will be moving in a clockwise direction from on the Smith chart. If we connect a capacitor in series, then also we will be moving in a clockwise direction. However, we will be moving towards the bottom side of the of a Z Smith chart, whereas for an inductive we will be moving up. For an inductive ZL, we will be moving upwards. So this is our point where we started initially, small z. On connecting an impedance and reactance ZL in series, what happens is this point traverses a constant resistance circle, since we are not changing the resistance, and it will appear at this point Z. Now let us see, now consider the other case. Suppose we have the same load Z, but now instead of an inductor we have a capacitance in series. Then what happens? Suppose this load is and this is ZC. We see that this is the initial Z that we had, just like in the previous slide. But then on connecting a capacitor in series, what happens is that this Z becomes a new value Z in, and the locus that we travel when we move from Z to Z in is along a constant resistance circle and in a downward direction. So when we have an inductor in series, then we move in a clockwise direction upwards, and when we have a capacitor in series, we move in an anti-clockwise direction downwards. Let us now consider the case when we have inductor in shunt with a load. So if we have an inductor in shunt, suppose we again have a load y equal to 0.5 plus j 0.5, and we connect an inductor in shunt as shown. Then what happens? Now this is, of course, this is a ZY Smith chart. The red lines belong to the Z Smith chart, the green lines belong to the Y Smith chart. And I had mentioned earlier that in a ZY Smith chart, if you plot a particular impedance with respect to the Z Smith chart, then it will also be the correct position with respect to the Y Smith chart. So here we have this impedance or admittance Y, and on connecting an inductor in shunt, a locus of this Y will move along a constant conductance circle till it reaches this point Y in. And finally, let us consider the case when we have a capacitor in shunt, with a load. So, say our y is equal to 0.5 minus j 1.0 and this is yc. What will y in be? And we see that on connecting a capacitance in shunt, y traverses in the anti-clockwise direction along a constant conductance circle till it reaches the point y in. Now, essentially what we would like you to understand is that when we have a capacitive load, whether in shunt or in series, we will always move downwards, and when we have an inductive load, whether in shunt or in series, we will always move upwards. So that was so this is the way we move along the Smith chart. Now, when it comes to designing matching networks for an amplifier, let us suppose our amplifier is like this. Say it has a transistor, some transistor inside it. Now, your generator will have certain input impedance Rs, and there will be some load RL. Your transistor needs to be properly matched at the input as well as the output. Now, at the input, therefore, we need some kind of network to act as an interface between the generator and the transistor, and similarly at the output of the transistor also we need a network which will act as an interface between your load and the transistor. Now, this network that is there between the transistor and the load is called the output matching network. And this network which is there between the generator and the transistor is called the input matching network. Now, so our input and output matching network has to be properly designed so that the output impedance that we see here is converted to this generator source impedance. Similarly, here also my output matching network has to be designed in such a way so that at the output of the transistor, whatever impedance exists, that is the output impedance of the transistor, is converted to the load impedance. How do we do that? So, to understand the way in which we can do this, let us see again an example. So, we already saw that when we have an inductor in series or shunt, we can shift our impedance or admittance, and they will be shifted upwards in a ZY Smith chart. When we have a capacitor in series or shunt, the impedance or admittance will be shifted downwards in a ZY Smith chart. Therefore, let us consider that we have an impedance. Here, of course, all the impedance and admittances that we are considering are normalized impedances and admittances. Let us suppose we have an impedance Z given by, let me write it properly. And we want to have some network in between so that we finally realize a 50 ohm impedance at the input of this network. Now, to do this, let us consider our Smith chart. Our Z equal to 0.5 minus j 1.0 is somewhere here on this ZY Smith chart. This is of course open, this is short, this is a ZY Smith chart. So from here we will have to bring it to the center, because this is the point corresponding to Z equal to 1. This is the normalized impedance, and normalized impedance corresponds to whatever our characteristic impedance is. In this case, suppose our Z0 is equal to 50 ohms, then this point will correspond to the Z equal to 1 or the 50 ohm point. So let us see now. So this is where we were starting from. This is Z equal to 0.5 minus J 1.0. Then if we connect an inductor in series, then as I had mentioned before, we will be moving upwards, because the upper part of the ZY Smith chart is inductive and the lower part is capacitive. We will be moving upwards along a constant resistance circle till we reach this point, say Z in. So at this point the input impedance is Z in or Y in. Y in if we consider the Y Smith chart in the ZY Smith chart. And then after that, now see, once we go from here to this point, we have to come back to this point at the origin. So to come back, we need to move in a clockwise direction once again, but then we need to go downwards. To do this, as we have learned earlier, to go downwards, we can use a shunt capacitance. Then this shunt capacitance will move downwards along this constant conductance circle. Now, how much inductance do we connect here, so that we go from here to here, and which constant conductance circle do we choose here? We choose that constant conductance circle that corresponds to the real part of Y being 1, or the G equal to 1 circle. So we connect that much inductance in series, so that this Z goes up till the edge of this G equal to 1, this green circle where conductance is 1, and then we connect another capacitance in shunt, so that we go along a constant resistance circle. I beg your pardon. We go along a constant conductance circle till we reach the origin. So how much capacitance should we connect here in shunt? We should connect that much capacitance that will cause the locus to move from this point Z in to the origin. Now you might have asked me that why restrict ourselves to this path only? There can be other paths as well. And absolutely. In this slide we saw that we are going like this and then coming like this to the origin. In this slide we show another path. We are first going along a constant resistance circle like in the previous case, but then instead of touching the G equal to 1 circle at this point, here we touch at this point, and from here we see that we have a path along this constant conductance circle where G equal to 1 to the origin. So from here to going from this point to this point, we connect a series inductance as we did previously, but then for going from Z in this point to the 50 ohm point, we have to travel along the G equal to 1 circle, but then upwards. So upwards means we have to connect an inductor in shunt, and that is what we have done here. Now let us see another example. We have a load 0.5 plus J 1.0 as shown, and again we have to match this impedance or admittance to the origin. So this is the basic setup. This is our Smith chart. This is where we start from, and this is our destination. So, the first method, we first travel along a constant resistance circle. Now, look, this point is upwards than the origin. So, we have to go downwards. So, first what we do is we go downwards along a constant resistance circle, and then touch the G equal to 1 circle at this point. Once we touch the G equal to 1 circle at this point, we note that if we go along the G equal to 1 circle, we can reach the origin. So, if we are going downwards, that means we have to connect a capacitance in series, and then once we are going downwards along a constant conductance circle, we again have to connect a capacitance, but in shunt. So, that is how it is shown. Now, what with the values of these capacitances can easily be computed from these constant reactance and constant susceptance lines. For example, the capacitance value here is that so we start from a constant reactance circle of 1 and reach a constant reactance circle of 0.5. So, the capacitance value will be the difference between the two, and so the YC, so we need a YC of 0.5 ohms for this series, for implementing this series impedance. And then here we go from -1 susceptance to -0.5 susceptance. So, again here we need a YC I beg your pardon, here we go from -1 YC susceptance to 0 susceptance. So, we need around 1 ohms of capacitance of susceptance to be present in shunt. Now, it is not always possible to obtain a solution. For example, if we have this kind, if we have a load where we would like to connect a matching network like this, that is an inductor in series and an inductor in shunt after that, then if that load is in this region shown by this shading marks, then we will see that for no value of these load can we obtain a matching network. Because see, if we connect, because if we have an inductor in series, then that means we have to travel along a constant resistance circle first, and then we have to come down by a constant conductance circle, which is not possible. Similarly, if we have this kind of matching network where we first have an inductor in series and a capacitor in shunt after that, then that is also not possible if we have our load anywhere in this shaded region. There are various ways of implementing a matching network, and we can use the Smith chart, that is the ZY Smith chart, to know the correct values of the elements that are required for implementing a matching network. Now, of course, all the networks that we showed so far are based on lumped element networks. So, how do we go from lumped elements to microstrip or distributed elements, which we have to use when we are in the microwave domain? So, let us see this example. So, one problem in realizing, if you see all the inductors and capacitance which we have discussed so far, we have considered them to be ideal. If we have an ideal inductor in series, then we see that we can go along a clockwise direction along a Z Smith chart, and if we have an ideal C in shunt, then we can also go along a clockwise direction in a white Smith chart. But in for real elements, what happens is that there is often a lot of resistance associated and so instead of getting a response like this, we end up getting a response like this. Now, microstrip matching network is an example of a transmission line where the Z0 and Vp are given like this. Microstrips are often used for implementing these matching networks. So, let us see how to do a matching using a microstrip line, because microstrips are as we have discussed, are a very popular method of realizing transmission lines. They are easy to fabricate, and they are also simple to understand, because they have a direct relationship with the, for example, the longer the transmission line, longer electric length of a transmission line translates to longer length in a microstrip line. Then the characteristic impedance of a microstrip line is related to the width of a transmission. The width of a microstrip line is related to its characteristic impedance. That is, if it is wider, then it has lower characteristic impedance. If it is thinner, then it has higher characteristic impedance. Now, if we go once again back to the slides on the monitor, then one common way of implementing using a microstrip line would be, if we choose a high impedance line of short length, then it can act as an inductor. If starting from this equation, if the electrical length beta L is less than pi upon 6, then we can show that Zin will be equal to this value. So, this is one way of achieving impedance, achieving a inductor that we had discussed a few minutes ago. Or if we use a low impedance line, that is the one that has low value of Z0, then also we can show that it will act as a capacitor, because for low values of beta L, that is when beta L is less than pi by 6, the Y in simply reduces to this value, which is like having a capacitance in shunt with the load. So, this entire line becomes equivalent to this line. And this is one diagram of how microstrips are used commonly. Now, in this module, what we discussed were how we can use a microstrip to realize the lumped L and lumped C that we discussed while that we saw are necessary for realizing the impedance matching network. And we also said that a high impedance, short length of high impedance line can act as an inductor, and it can substitute for the inductor, or a short length of low impedance line can act as a capacitor, and it can be substituted for the capacitor. But then that is not all. In the next module, we will see that how purely from a transmission line perspective, rather than substituting an L and C with short lengths of microstrip line, whether we can use a normal that is a microstrip line which has the same characteristic impedance as that of the input and as that required for impedance as that required for input and output impedance matching, but its length, by varying its length, we can achieve the same impedance matching. Thank you.